so thanks for the introduction. And this is a joint work with Professor Elchanan Mossel from Penn and UC Berkeley. Okay. So I'm going to talk about the stochastic block model. And again, I'm also going to look at a very simple form of stochastic block model. Suppose we have n nodes in total, and which are divided into two communities of equal size, n over 2. And then for two nodes within the first community, they are connected independently with edge probability A over n. And then for two nodes which are, both of them are in the second community, they're connected independently with edge probability C over n. And then for two nodes not in the same community, so they're in two different communities, they're connected independently with edge probability B over n. Okay, so on the left-hand side, I show you this is a plot of the adjacency matrix. Since we have two communities, this corresponds to two diagonal blocks. And on the blocks, the entries are Bernoulli with parameter A over n, or C over n, or B over n. Okay? Then the problem is that given such a single realization of the graph or the adjacency matrix, the goal is to recover the underlying true community partition. And this has been mentioned in the previous two talks. So there has been a remarkable progress on this problem in terms of identifying recovery thresholds. In particular, they look at a symmetric case where the edge probability within the first community equals the edge probability within the second community. So that's A equals C. Then let epsilon to denote the fraction for misclassified vertices. Then the first result talks about the correlated recovery, which asks that epsilon to be strictly bounded away from 1/2. So that is like do better than random guessing. And it was shown that the correlated recovery exhibits a sharp phase transition threshold. And then above the threshold, correlated recovery is possible in polynomial time. And then below the threshold, correlated recovery is fundamentally impossible. Okay? So just remind you, the A over n is the edge probability within the first community or the second community. B over n is edge probability across two different communities. So when A equals B, then there's no information. So this condition is violated. So when A is differs from B, then the condition will be satisfied. Okay? And then you can ask the similar thing for the weak recovery, which requires the epsilon, so that is the fraction for misclassified vertices, go to 0 as the number of nodes n goes to infinity, and a similar phase transition threshold has been shown. So in particular, you can think of the left-hand side as a signal-noise ratio. Here you want a signal-noise ratio goes to infinity as you increase the number of nodes. Okay? And then we can also look at the so-called exact recovery, which essentially is saying that there's no error at all with high probability. And then so like similar result has been shown for the sharp phase transition threshold. Okay? So for this talk, actually, we're going to ask a little bit more refined question. So that is, what is the minimum possible epsilon that you can get for a particular model parameters like A, B, and C? Okay? So this leads to the main result of this talk. So essentially, we're showing that if the average degree of the graph goes to infinity, but at a slower rate than n to the power of little over 1. So for example, like log n. Okay? Then the minimum possible epsilon, so that is the minimum possible fraction for misclassified vertices you can get, can be characterized through this simple formula. So Q here is the complementary CDF of a standard normal distribution. And V star is the unique stable fixed point of the following fixed point equation. Okay? So A over n is edge probability within the first community. C over n is edge probability within the second community. B over n is edge probability across two different communities. And Z here is the standard normal distribution. Okay? So far clear? Okay? So I just want to make two remarks. So if A equals C, so if A does not equal C, so then the average degree of a node in the first community is different from the average of a node, average degree of a node in the second community. So the degrees are correlated with the underlying true community partition. Okay? In this case, the minimum possible epsilon can be achieved very efficiently in linear time using the Belief propagation running on the local neighborhood of every vertex. Okay? And if A equals C, so that corresponds to the symmetric case where the degrees are uncorrelated with a true community partition. In this case, the minimum possible epsilon can be achieved using local Belief propagation plus the correlated initialization provided by correlated recovery. Okay? So in the rest of the few minutes, I'm just trying to show you how we prove this theorem. So the one key and a very well-known fact is that if the average degree goes to infinity not so fast, then the local neighborhood of any given vertex is a tree with high probability. In particular, it can be coupled with the following very simple two-type branching process. So here I use the blue node to denote a node in one community, and the origin node to denote a node in the second community. Then suppose the root node, so the color of the root node is chosen uniformly random, and suppose it is blue, then it will generate a Poisson number of children with the blue labels and the orange labels with rate given by A over n, or A over 2, or B over 2. Okay? And then I look at the orange children. It will also generate a Poisson number of children. So then the rate is given by B over 2 or C over 2. And then I just keep recursively generate this Poisson tree. And then this is locally, I can show that the local neighborhood of any given vertex can be coupled with this two-type branching process. Okay? So then the idea is that for the original community detection problem, I do not observe the colors of the label of the nodes. Okay? I only observe the graph structure. So I can look at, for given vertex, I can look at the local neighborhood up to a depth, certain depths. Then using the local graph structure, I can estimate the root, so the color of the root node. And this gives you an upper bound on the minimum possible epsilon that you can get. To get a lower bound, essentially we're using a Gini type argument. Suppose the Gini can reveal the exact colors at the boundary of the tree. Okay? And then I can show that given this information, I can neglect all the information outside of this local neighborhood. And then using this, I can, so essentially starting with the exact information, I want to estimate the color of the root node. This gives a lower bound on the minimum possible epsilon. Okay? And then for this two reconstruction problem on tree, so the optimal estimator is the maximum a posterior estimator, and this can be computed using Belief propagations. And then the iterations are just the recursive formula of log-like ratios. And then if these two belief, so the only difference is that the upper bound is initialized with the zero information. For the lower bound, the BP is initialized with the exact information. To show the upper and lower bound matrix, we only need to show that the belief propagation converges to the same fixed point. So to analyze that, we essentially look at how the distribution of the message evolve over time t. To do that, we're using the Gaussian approximation. So essentially, we're assuming that the belief propagation messages are approximately Gaussian with certain mean and variance, and then the mean and variance satisfy certain updated equations. Okay? And then to finish the proof, so we just first show that the mapping from V to this expected attention function is concave. And this immediately leads to that this VT sequence, no matter how it is initialized, the VT sequence will also always converge to the unique stable fixed point. And this will conclude that the upper and lower bound that I showed you earlier will be will match with each other. Okay? So that leads to the conclusion. Essentially, the takeaway for this talk is that for two equal-sized communities with a slowly diverging average degree, so the minimum possible epsilon can be characterized through a very simple formula, and it can be achieved efficiently as well. So the open question is that what happens when you have multiple unequal-sized communities? Okay, thank you.